In the previous lesson, low-pass and high-pass filters kept one side of the frequency axis. Now we keep the middle. A bandpass filter rejects very low frequencies, rejects very high frequencies, and passes a band around the center frequency. The new idea is resonance. An inductor and a capacitor can cancel each other's reactance at one frequency. A bandpass filter has three landmarks. The center frequency is where the response is largest. The lower and upper cutoff frequencies mark the -3 decibel edges. The bandwidth is the distance between those two edges. A narrow bandwidth means the filter is selective. A wide bandwidth means it is forgiving. The cleanest passive example is a series RLC circuit with the output taken across the resistor. At low frequency, the capacitor blocks current. At high frequency, the inductor resists rapid change. Between those extremes, the current can become large, so the resistor voltage becomes large. That middle region is the pass band. Resonance happens when the inductive reactance and capacitive reactance have equal magnitude. In formulas, omega naught equals 1 over square root of LC. At that frequency, XL and XC cancel in the series impedance, so the circuit looks almost purely resistive and the output across R peaks. On the magnitude plot, the bandpass curve rises from low frequency, peaks near the resonant frequency, then falls again. The peak is not magic amplification in a passive circuit. It is a voltage division result caused by the impedance becoming most favorable at resonance. The important reading is not only the peak, but also how quickly the response falls away on both sides. The -3 decibel frequencies are called omega 1 and omega 2. They are the points where the magnitude has fallen to 1 over square root of 2 of the peak value. The angular bandwidth is omega 2 minus omega 1. In hertz, the bandwidth is f2 minus f1. The quality factor Q compares the center frequency to the bandwidth. Q equals omega naught divided by bandwidth, or f naught divided by bandwidth in hertz. High Q means a tall, narrow, selective response. Low Q means a broad response. In a series RLC bandpass, Q also equals omega naught L over R. Phase gives another view of the same physics. Below resonance, the circuit behaves more capacitive. Above resonance, it behaves more inductive. At resonance, the reactive terms cancel and the resistor voltage is in phase with the source. Energy is still moving back and forth between L and C, but the net reactive impedance is 0 at the center. A quick design example. If L is 10 millihenries and C is 100 nanofarads, then F naught is about 5.03 kilohertz. If R is 100 ohms, then Q is about 3.16 and the bandwidth is about 1.59 kilohertz. Changing R is the easiest way to widen or narrow the passband. 3 traps. First, resonance frequency and bandwidth are different ideas. Do not mix them. Second, Q is not automatically good or bad. High Q is useful for selection, but bad if you need a flat, wide band. Third, real coils have resistance, real capacitors have loss, and any load connected to the filter changes the effective Q. Summary. A bandpass filter keeps a middle frequency band. In a series RLC bandpass, resonance occurs at 1 over square root LC. The -3 decibel points define bandwidth, and Q equals center frequency divided by bandwidth. Next, we use the same ideas to build a band reject filter and compare passive filter examples.